Okay, so I just put up real quick a summary of what it is we're doing. We only meet as a class three more times, including today. Go ahead. So today we're going to do integration by parts. And then on Tuesday we're going to do applications, which are word problems. And then next Thursday we're going to review for the final. And that next week is finals week, so we only meet one time. And we meet on Thursday for our final exam, which starts at 9:30, but ends at 12:15. Yes?
So is that's the final day?
Yep.
Okay.
The 10th. All right. So don't show up here on the 8th because we won't be here. All right?
It's the same timing, right? 9:30?
9:30 is when it starts, but we have until 12:15. Yeah. And you shouldn't have any other finals that overlap with this final. Unless perhaps you're enrolled in a different school somewhere.
My class for Tuesday is actually Tuesday. Instead of
Yeah.
Tuesday.
Yeah, they do that on purpose. Yeah. All right. Any questions on that? So you'll want to be here next week because all the different ways we're learning how to integrate is the sole purpose is so that we can do some applications. All right. And whatever we do here, if you still have questions on it, we can talk about that a little bit on Thursday also. So Thursday we'll talk about, what you should expect on the final. Yes?
When do you usually put up the videos for the day?
Same day.
That same day?
Mm-hmm. Yep, usually not till the afternoon because I have a class right after this. That ends at 12:40, and then I go to my office and I upload them. They're usually up by about 1 or 2. All right, so we get to discuss integration by parts. Last time we were doing integration by what we called substitution. And we saw that was a little bit problematic. I mean, y'all seem to get it, but I think maybe I helped convince you that it wasn't as straightforward as the power rule, which we just added the power up there, right? You had to try some things, and sometimes it wouldn't work, right? So integration by parts is even more challenging, right? It's even more difficult. So let's look at a problem first that we can't do, all right? And then I will give you, it's a formula, okay? The integration by parts is a formula that you'll use. It's a little tricky how you use it. So let's say we're trying to find the antiderivative of x times e to the x. All right? So by themselves, you could do this problem. In other words, if I asked you to find the antiderivative of x, is everybody comfortable with the idea that this would be 1/2 x squared plus some constant? That would just be the power rule? Yes? So by itself, you could do the x. Yes? Okay, by itself, you could do the e to the x. Because the antiderivative of e to the x is what? It's itself. All right? So we've talked about both of these things already. We've done them both. Yes? That's what we would do if they were just by themselves. But they're not by themselves. They're attached to one another with multiplication. What if there was addition between them or subtraction? Could we do them separately? Yes. Okay? But the problem is that there's multiplication in here. And when there's multiplication, you cannot just, unfortunately, you cannot just do them separately and then multiply the two answers together. You cannot do that. If you could, they'll actually make this topic a lot easier. Cal 2 would be a lot easier for my Cal 2 students because they wouldn't have to worry about that. But you can't, all right? So we are not allowed to do them separately. So how do we do it? Right now, we could try a substitution. Would you like to try a substitution? We have to pick something, and we're trying to see its derivative, right? Any ideas? If we try to do substitution on this? This is what we did last class, right? We have to pick some u and then take its derivative. So what would you choose for u? You could do x. right? I mean, just try it, right? But let me show you what happens if you do that. If you pick x, the derivative of u with respect to x, well, what is the derivative of x? 1, right? Then you multiply both sides by dx, and you get 1 dx. You don't need the 1 here, but it's there, right? So then you go try and rewrite the problem. What am I going to replace x with? U. U, e to the, I'm going to replace that x with u. And then what am I going to replace dx with? du. So, congratulations. You've just rewritten the problem, replacing all your x's with u's. But it's the same problem, right? Isn't that exactly the same? Nothing got better. So that substitution doesn't work. Any other ideas for substitutions? No? E to the x? Okay, good. Let's try that. So if we tried e to the x, the derivative of that, what's the derivative of e to the x? Itself. Okay. And then I multiply both sides by dx. So here's what I've got, right? So now I try and rewrite the problem. What am I going to replace x with? Well, I never have anything over here that has x equals something, do I? I don't, right? So I can't replace this x with anything. Now, could I replace the e to the x with something? Yeah, I could replace it with u, so I would have x maybe. I could replace e to the x with u, and then dx, I have to replace it, I'd have to solve for this, right? So then I have to divide both sides by this. Basically, it's not going to work because this x I can't get rid of. Does that make sense? And the whole idea last class with substitution was to change everything from x's over to u's, do the integration, and then switch your u's back to x's. So we are definitely jammed up here. There's nothing we can do. All right? Are y'all convinced? Okay, so there hopefully is a way to do this, but it requires a brand new technique. And it's called integration by parts. So I have to give you the formula first, and the formula is going to make you a little ill. All right? So here's the idea. I'm going to erase this. We'll come back to it. Here's a formula. Let's say that you're trying to integrate something, and you have something times the derivative of something else. Now, let me stress to you what's happening here. U is just something, some expression, all right? And then d, this is a v, not a u, okay? dv is the derivative of something else. So I'm going to point this out, illustrate this. This is some function of x, and then this is some, no, let me not say some. Let me say this is the derivative of some other function of x. So just bear with me for right now, okay? Let me write the formula out, and then when I do an example, hopefully you'll see it, all right? So what we have is some function of x. Maybe this is x squared. Maybe this is e to the x, something, right? And then this one right here is the derivative of some other function that is totally unrelated to this function, but it's the derivative of something, all right? The integration by parts formula says that this is equal to u times v minus a new integral v times du. That's the formula. What? What? All right, let's see if we can't figure out what the heck this is saying. So we have some function that has x's in it, right? Then we got the derivative of some other function sitting next to it. This formula says that this is equal to this u right here, right? Same u, times not this, but what? What do you think v is? If this is the derivative of some function, what is v? It's its antiderivative. You see that? So if this is the derivative of v, and this is v, that means that right there is the antiderivative of this. All right? So it's the product of those two minus a new integral. We still have to do an integral, so unfortunately this formula doesn't take the integral away, it just allows us to do a new integral. But do you see the difference in this new integral from the original one? What's the difference? And this is the key to integration by parts. What's the difference between these two integrals? This one is v, right? This one had what? The derivative of v? And this one has the derivative of u, but this one had u. So do y'all see that they like switch places? It's like here you had u, but in the new integral, it's the derivative of u. Here you had the derivative of v, but in the new integral, you have the antiderivative of v. And believe it or not, a lot of times that switching allows us to be able to do the problem. All right, that's the whole key to the whole thing. In fact, I remember when I was a student learning this technique, my professor was very theoretical, and he was like, I want you to look at integration by parts as a transferring of the derivative. You're transferring the derivative to one of the functions, and you're basically transferring it off of the other one. So this is a derivative, but in the new one it's gone. This one's not a derivative, but in the new one there is a derivative. Now there's a way you can remember this formula, all right? There's a little cute little, like, I don't know if it's not really an acronym, but it's a cute little saying. Ultraviolet minus voodoo. I think that's the way you spell voodoo. Ultraviolet minus voodoo. I don't know why, but a lot of students can remember that, ultraviolet minus voodoo. But here's where it is. Ultraviolet minus voodoo, right? Now you have to remember the integral sign, but ultraviolet minus voodoo is the formula, all right? All right, let's see how we can maybe make this thing work. Let's see if we can't make sense out of it. All right, we have the problem that we were stuck on, e to the x times e to the x dx. We already know that substitution's not going to work. We tried it and it didn't work. So the only other thing we have is this, all right? So what we need to try and see here is, do we have a product? Well, we do, right? We have two things being multiplied. One of these things I'm going to try and call my u, and the other thing needs to be the derivative of some function, all right? So I really have two choices here. I can let the x be the u, right? Or I can let the e to the x be the u. Do you see I have two choices for u? Now, which one would make more sense to pick as u? And why? This is the key part. And why? Why?
Because it would multiply by the derivative of x, which is just 1, so it turns into e to the x.
Okay, so if I pick my u to be x here, right? What happens to it in the new integral? It's its derivative, right? And what's the derivative of x? 1. So in the new integral, the x is gone. Do you see that? That's a good thing. Because isn't that what's kind of causing the problem here? Like if it was e to the x by itself, we could do it. But because the x is there, it's trouble. So if I pick my u to be the x, in the new integral, it's 1. Right? So I'm going to just kind of highlight under this. I'm thinking right now that this right here is going to be my u, which forces me, I have no other choice, but to make this, everything I see there, my dv. Do y'all see that? Now let's think about it. Is that okay? In the formula, the dv part is going to switch over. In the new integral, it's going to become what? V, right? Which is the antiderivative of this? Do you know the antiderivative of this? Just that. That's dv. Do you know it's antiderivative? It's e to the x, right? That will be in the new integral. So in the new integral, I'm trying to get you to see this like ahead of time before we do it. What's going to happen? If we pick this to be u and dv, in the new integral, we're going to have a 1 and an e to the x, aren't we? And that's good. It's just e to the x, and we can integrate e to the x. Okay, so that's kind of the beginning. Let me show you the formal way that I do this. Every time I do an integration by parts problem, what I do is I set up a table. Right, this is just the way I've always done it. And what I do is I put u here and dv down here. This is how I start it. And now I make my choice. What did I want my u to be? I want it to be x, so I'm going to say u is x. And then what did I choose my dv to be? You have to pick the whole thing, okay? Everything that's left. So e to the x dx, right? Y'all good with that? Okay, so from this table, the way it's going to work is once you pick your u and your dv, you're going to basically differentiate down. So here I'm going to take the derivative of u with respect to x, and then over here on the table I'm going to integrate to come up. So I'm going to take a derivative, the derivative of u with respect to x down here, it's going to go here, and then here I have to take the antiderivative, and that will take me back up to v. Does that make sense? So let's start with this. What is the derivative of u with respect to x? We just said it would be what? 1? Y'all good with that? And if I multiply both sides by dx, I get du is equal to dx. So I just multiply both sides by dx. Y'all good with that? Sure? Okay, and then here when we integrate up, what's the antiderivative? So I'm basically saying this, hey, do the integral of just this and bring it up here. And what's that answer? E to the x. Now we will have a plus c, but I'm just going to throw a plus c on my answer at the very end. When I'm done with this formula, at the very end I'm just going to go plus c. All right? So I'm not even going to worry about it right here. Okay, any questions on how I did that or how I chose things? Sure? All right, here we go. This integral is equal to ultraviolet minus voodoo. U times v. So you go to your table, what's u? X times v, what's v? E to the x, right? So it's x e to the x, then minus the integral of v times du. V was e to the x, and du is dx. And do y'all see that we can now find the antiderivative of this, right? So this now becomes, that equals x e to the x minus the antiderivative of e to the x was what? Itself, e to the x. That's it, right? Plus c. This is the antiderivative. What do y'all think? First time through, what do you think? First problem, that seem okay? It all comes down to you picking the u and the dv correctly. You've got to be able to get this table set up correctly for this to work. Now, do you believe that we got the right answer? Do you believe that this is correct? Well, we could check it, couldn't we? How could we check it? Take the derivative of it, right? And if we take the derivative of this, we better get back x e to the x. That was the original thing we were trying to integrate, right? To find the antiderivative of. So I'm going to do that real quick. I'm going to take derivative of this. Do y'all see that we have a product right there? So we'd have to do product rule. So if I do product rule here, it's going to be derivative of x, which is 1, times e to the x, plus the derivative of e to the x, which is e to the x, finish off the product rule, times x. So that's my product rule right here, right? So I'm done with that. Now minus the derivative of e to the x, which is e to the x. And do you notice here on the front I've got an e to the x, and on the back I've got a minus e to the x? And do you see how these just cancel? And what are you left with? E to the x times x, which is x e to the x, which is this. So it works, yes? It worked this time. All right, let's do another one. What I'm going to do at the end of class is I'm going to give you a few problems up here on the board, and they're going to be a mixture of problems that require either substitution or integration by parts or just power rule. So the challenge is going to be to figure out which one of these methods you need to use. All right? And that's something that you need to prepare yourself for on the final. Like, I'm not going to give you a problem and say, find the antiderivative using integration by parts. Like, I'm not going to tell you that. And that's what makes it hard. Do you understand that? If I tell you use integration by parts, you kind of know what you need to do already. But for now, the problems I put up here are integration by parts problems. So here we go. Next one. Let's first realize that we cannot use our basic power rule, and that substitution is not going to work either. That's hard to, I think that's hard at this point because you just did substitution 2 days ago. It's hard possibly for you to see that. Those won't work. You might have to actually just try. But the main thing with substitution was, do you see something and its derivative there? Does anyone see something in its derivative? Not really, right? If you said, hey, I'm going to let u be x squared, the derivative is 2x. And I don't have a 2x here, right? I do have an x here, but it's inside of a natural log, so it's not really like free by itself. If you pick natural log of x as u, what's the derivative of natural log of x? The derivative of natural log of x. Do you see 1 over x anywhere? No. Right? So do you see how substitution just doesn't seem like it's going to work? Okay. So let's do integration by parts. Let's try that. We have to pick a u and we have to pick a dv, right? So I'm going to start with my table. I'm going to put u here. I'm going to put dv here. And now we get to pick. All right, anybody want to take a shot at this? What I'm asking is someone to tell me what you want me to have my u be, and what you want me to have my dv be, and why you want that. I also want the why you want to do it that way. Anyone have an idea? Go ahead.
The u will be the x squared.
U is x squared. Okay, let me put that down. And then dv would have to be what? It would have to be the ln x dx. Make sure you bring the dx. So you've basically broken it up like this. This piece and this piece, right? There's your multiplication. You've said, I'm going to let u be this, and I'm going to let my dv be this. Yes? Does that seem reasonable to everyone? Yes? Okay, now I wanted the reason why. Yes?
What if you just did it the other way?
What if you did it the other way? I think what you mean is, what if you let the u be the natural log of x and let this part be the x squared? Let's get to that. We're actually going to see that's actually the right way to do it.
Yeah,
But let's see why now.
I see now.
You see why?
It would be easier to take the derivative because it'd be 1 over x.
Yeah, so look, u being x squared works out real nice on this step because you're going to have to take the derivative of this, right? And that's just 2x, yes? The hard part now is you have to go and you've got to take this and integrate it, right? Antiderivative of natural log x. We do not have I've never told you what the antiderivative of natural log of x is, have I? Never have. I've told you what the derivative of it was, right? But not the antiderivative. It's x natural log x minus x. Yeah. But we can actually come up with that formula ourselves right now if we wanted to. But let's just wait. Okay, so do you see here, this was a good choice for you. But the dv part going up can't do it. Yes? So let's try it the other way. All right, let's switch it. So instead, let's put the natural log x here, and let's put x squared dx here. Notice that the dx is always going to go with the dv one. All right? So I just put that natural log x. The way I broke it up is like these two are together, x squared dx, and the natural log of x is going to be my u. Now let's think about what would happen. We're going to take the derivative of natural log of x, right, to go from here to here, and we all know what the derivative of natural log of x is. Then we have to take the antiderivative of x squared and go up, and we know that also, right? 1/3 x cubed. Okay, so this looks promising. Let's go ahead and do it. This is du dx equals 1 over x. That's the derivative of this. And then multiply both sides by dx, and you get 1 over x dx. So that side's done. This one here, we want to integrate to go up to v, and that's 1/3 x cubed. You're all comfortable with that, right? So before I continue, I want to make sure that we're not going to be stuck. The formula is ultraviolet minus an integral, right? Voodoo. Voodoo is v du. V du. Here's v. Here's du, right? In my new integral, the new integral that I'm going to come up with, it's going to be this times this. Is that going to be something we can handle? What happens if you take x cubed and divide it by x? You just get x squared, right? I can integrate x squared. So what I'm doing is, I'm thinking ahead, and I'm saying in the new integral I'm going to have v times du, and that is something I'm happy to see. When I put these two together with multiplication, I will be able to handle that integral. So I'm going to keep moving, keep doing this. This integral becomes what? Ultraviolet, right? So what's that? What do I write down here? ln x times 1/3 x cubed, okay, minus integral, and then v du. So 1/3 x cubed times 1 over x dx. And what is this? When I put those together right there, it's just x squared, right? That's x cubed over x. One of the x's cancel, we get x squared. So here's where I'm at. All I did is rewrote this. We usually like to put this thing out in front of the natural log, so I went ahead and did that. And then I have minus integral 1/3 x squared dx. What's my next step? Find the antiderivative, right? Find the antiderivative of x squared. Now, what's going to happen with this 1/3? It's going to come along, right? It's going to come along for the ride. So I have the 1/3 x cubed out here, natural log x, minus, now I'm taking the antiderivative at this point, so the integral sign is going to go away. The 1/3 comes for the ride, and now the antiderivative of x squared is what? 1/3 x cubed. So you'll have another 1/3 there. And now you can slap your c on there, plus c. And I suppose there's one more step. We could put the 1/3 times 1/3 together and make it 1/9. And we'd be done. You could always check your answer by taking the derivative of this. you would have to do a product rule right here. It'd be a little messy, but when it's all multiplied out and cleaned up, you should get back x squared natural log x. All right, what do y'all think? That was the second one. Huh? Hmm? All right, so since you asked, or I don't think you asked, but since we mentioned it, what would the antiderivative of natural log of x be? I just told you what it was, but I didn't expect for you to memorize it just by me telling you.
Was it natural log x minus x?
Yes, x natural log x minus x, but where did I get that from? Let's see. All right, so here we go. You don't have a basic formula like the power rule here, right? Substitution definitely won't work because there's only one thing to pick for substitution, and that's natural log of x. And the derivative of that is 1 over x, which doesn't appear here. So power rule and substitution, throw them out the window. That leaves us with one other thing, and that's integration by parts, right? So then we have to come up with this table, and we have to pick a u, and we have to pick a dv. What do you think?
U would be ln x.
Yeah, I mean, you really only have one choice here, right? ln x would be our u, that's this piece. And that only leaves one thing for dv, and that's what? Just 1 dx, if you'd like. You'd write it like that, 1 dx, or just dx, right? So this part becomes the dv. What's the derivative of u? So when I come down and do the table, I have du is 1 over x, dx. I went ahead and did du dx, and then I multiplied both sides because we just did that. So du is 1 over x dx. What is the antiderivative coming up like this? What's the antiderivative of dx? This is a little tricky. Just x. Think about it. What's the derivative of x, everyone? 1, right? So the antiderivative of 1 would be x. Make sense? All right, ultraviolet minus voodoo. What's ultraviolet? These two multiplied, right? I'm going to put the x in front. Minus integral v du, right? v du. So v times du. You all see that? And what happens with those x's? They cancel, right? So you get x ln x minus integral. These x's cancel. That's just 1 dx. And what's the antiderivative of 1? We just did it, x, right? So this is going to be x ln x minus, this integral is x plus c, and we're done. You could check it by taking the derivative. There's a little product rule here, and when you take the derivative of this, you get natural log of x. It's kind of interesting, huh? Yeah? Okay, how about this one? Okay, what's different about this problem? Yeah, you have those numbers on the integral signs now, right? And that was that fundamental theorem of calculus thing I showed you a while back. It's been, I think, 2 lectures since we talked about that. The first step to doing this is to find the antiderivative. That's the first step. So if I find the antiderivative, I have to find the antiderivative of that, right? Which we just did. We just did that work, so I'm not going to redo it. So what we did is we wrote down x ln x minus x plus c. And then we put that bar over here and we put 1 in e. Do you remember me doing this? It has been a few classes, but does that look familiar to you? It's in your notes? Are you looking? Is it in there? Okay. You should have something in there. What did we do with this? We find the antiderivative, then we put this bar here, and then what does that mean at this point? What do I do? I plug in the e into this, and then I put minus, then I plug in the 1 into this. Does that sound familiar? Familiar to you? Yes? Okay. Pardon? Yes, f of b minus f of a. Yep, f of b minus f of a. So what I'm going to do now is I'm going to take the e and plug it in here for x. So that's going to be x e natural log of e minus e plus c. That all rhymes. E natural log of e minus e plus c. Okay, that's just e going in for all the x's, right? Minus, now what am I going to plug in? The 1. So I have 1 times natural log of 1 minus 1 plus c. So the only difference between this problem and this problem is that at the end, after you find the antiderivative, you actually have to evaluate the antiderivative at the two endpoints. And now we need to see if we can't figure out what this is. You might need your calculator for this. Does anyone know what natural log of e is? It's 1. Okay, natural log of e is 1. So you might need your calculator for this. This is 1. This is e, right? So e times 1 is e. Minus e plus c. Okay, because this is 1. Then minus, anybody know what natural log of 1 is? 0. So this kills this off. 0 minus 1 plus c. And now some things start to cancel out. I get the e's are gone, right? So all I get is c there. Then I have my distribution of my negative through here. So minus becomes plus 1, and minus c becomes minus c. And the c's cancel, and your answer is 1. Now you may have forgotten about this. Because I mentioned it over a week ago. But what this is saying to us is this. If you were to look at the function natural log of x, it's a function that you can graph. It looks like this. That's what natural log of x looks like if you graph it. If you were to look between 1 and 0, so 1 is here, sorry, not 1 and 0, between 1 and e. So 1 is here and e is out here. If you were to try and find the area underneath this curve, the area under that curve is what? Is 1. Is 1 unit. That's what we just did. We found the area below the natural log function between an x coordinate of 1 and e. And the area of that is exactly 1 unit. All right, that's what we're doing. Okay. You ready? Your turn. It's 10:11. I'm going to put some problems on the board here, and there's going to be no instruction as to which technique to use. And you get to work together and see. Pardon me? Everything. So you can use power rule, substitution, or integration by parts. Okay? First one. X e to the negative x dx. Second problem. X e to the x squared dx. Third problem. X squared over x cubed plus 1 dx. Next one, this one's going to be probably the hardest. Well, yeah, this is probably going to be one of the harder ones. All right, there you go. There's 6 mixed problems that require either power rule, substitution, or integration by parts. And let me just warn you that if you start trying to do integration by parts on a problem that required substitution, you're going to create a mess for yourself. If you try and do, bless you, if you try and do substitution on a problem that needs integration by parts, you're going to be, just going in circles. So I told you last class, you're going to fail more than you succeed. You're going to try things and it's not going to work. Just be prepared for that, all right? But what I'd like to see is you talking to your classmates, trying to figure out what the approach should be for each one so that you can start to try and identify what you need to do, all right? Okay. Enjoy. I'm going to kill the camera because I don't think there's anything else here I need to discuss.